What if I told you the next generation of power plants might run on carbon dioxide, not as a pollutant, but as a high-performance working fluid, with turbines so compact a multi-megawatt unit can fit in a surprisingly small footprint? The secret is a weird state of matter called supercritical CO2. CO2 becomes supercritical above its critical point, 31.1 degrees Celsius and 7.38 megapascals. Past that point, it's no longer a clear liquid or gas. It becomes a single-phase supercritical fluid, dense like a liquid, but it flows like a gas. In normal gas turbines, compressing air takes a lot of energy. But near the critical point, CO2 behaves differently. Its compressibility factor drops sharply, meaning a small amount of compression work gives a big density increase. That high density matters because compression work is lower and the backwork ratio can be around 0.18, compared with 0.40 to 0.50 in air Brayton cycles. The turbomachinery can be much smaller. The attachment notes SO2 turbomachinery can be around 1/10 the size of steam equivalents at similar scale. There are two big ways supercritical CO2 power plants are built. Indirect heating cycles, where CO2 is heated through a heat exchanger using nuclear heat, solar thermal, or industrial waste heat. The most common architecture is the recompression Brayton cycle. Direct-fired cycles, where fuel is combusted with oxygen directly in a CO2-rich working fluid. The most famous is the alum FETVET cycle. At its core, an indirect SCO2 plant is a closed Brayton cycle. CO2 is heated in a primary heater/primary heat exchanger. It expands through a turbine to generate power. Heat is recovered in recuperators. CO2 is cooled, then compressed and sent back for heating. Here's where SCO2 gets tricky. Near the critical region, the specific heat of CO2 can spike. That creates a mismatch between the hot turbine exhaust stream and the cold compressor discharge stream inside the recuperator. That mismatch causes a pinch point, a section where the temperature difference becomes tiny, limiting heat transfer and choking efficiency. This is exactly why the industry moved to the recompression cycle. The recompression cycle solves the pinch point by splitting the flow. After the low-temperature recuperator, the low-pressure CO2 stream splits. About 60 to 70% goes to the precooler and then the main compressor. About 30 to 40% bypasses heat rejection and goes to a recompressor. Then those two streams are mixed, ideally at similar temperature and pressure to reduce losses. After mixing, the combined stream is preheated in the high-temperature recuperator, then heated again in the primary heat exchanger, and finally expanded through the turbine. The split is the magic variable. By reducing mass flow through part of the cold side of the recuperator, you better match the heat capacity rates, mass flow time specific heat, so heat transfer stays efficient and the pinch point is reduced. That's how recompression pushes SCO2 cycles into the 45 to 50% plus efficiency band at high temperatures, according to the comparative table in your attachment. SCO2 plants are heat exchanger heavy. Recuperators are a major driver of performance and cost. That's why many designs use printed circuit heat exchangers, microchannels etched into metal plates, stacked and diffusion bonded into a strong block. They're extremely compact and can achieve very small approach temperatures, great for efficiency. But the tiny channels mean you need excellent fluid cleanliness and careful thermal ramping. The turbomachinery is compact, but the environment is intense. High pressure, high speed, and unusual fluid dynamics. Sealing is a big deal. For example, dry gas seals need to seal gas to stay above the critical point. If it drops into two-phase conditions, liquid droplets can damage seal surfaces and cause failure. Now for the direct-fired cousin. The alum cycle burns natural gas with pure oxygen from an air separation unit, but uses a massive recycle of high-pressure CO2, around 95% of the flow, to control combustion temperature. After expansion, the stream is cooled so water condenses out, leaving a nearly pure CO2 stream. A small portion of CO2, around 5%, is taken off at high pressure for transport or storage, while the rest is recycled. The big promise: power generation with inherent CO2 capture architecture. Supercritical CO2 power blocks are attractive because they can deliver high efficiency at high temperature ranges, smaller footprints, and potentially faster modular deployment. Very low water use potential because dry cooling is feasible in SCO2 heat rejection designs. This is why SCO2 is often positioned as an enabling technology for SMRs, CSP with dry cooling, and industrial waste heat recovery, the places where power density, water limits, and efficiency matter most. So the headline is simple. Supercritical CO2 power plants replace the steam/water paradigm with a dense, single-phase working fluid. The recompression cycle solves the recuperator pinch point. PCHEs make the heat exchange compact, and advanced seals and materials keep the system stable at extreme conditions. If you'd like, I can also break down where SCO2 plants are economically strongest, waste heat, nuclear, or CCS, and what the real-world constraints are for each. Subscribe for Energy News Daily. Next, SCO2 versus steam rank in real projects.